All right, let's get started. So I'm going to briefly go over solutions to the breakout section that we started on yesterday afternoon. And in case you don't know, I'm Eric Pettigura. I'm one of the counselors here. All right, so we're going to be working in IPython. So from my terminal, this is the directory where my notebooks are stored. You see them here, trapezoid rule and homework 1 solutions. We'll be going over that later. So I'm going to fire up the IPython notebook with this incantation here. And then notice this -- pylab inline. And inline basically lets you display plots right in the notebook.
Eric, can you get some of the lights?
Sure.
In the middle of the chalkboard. Below the middle of the chalkboard. Just to your right.
Oh, okay. Here.
Yeah.
That good? All right, so we're going to fire up the IPython notebook. It's going to open up a web browser, and let's take a look at the solutions. So the trapezoid rule is sort of the next level of sophistication to computing the area under a curve beyond just the strict Riemann sum. So you're basically, with the trapezoid rule, you're just computing the average value at a bunch of different step sizes and then summing those up times the width of the step. So coding this up is fairly simple. It's a one-line, it's essentially a one-line call. And the only thing that you need to be sure that you understand about this piece of code over here is the way that the slicing syntax works. So is everyone clear on what this 1 colon and colon minus 1 do? All right. Would somebody care to explain what that does? Sure.
So the 1 colon takes everything starting with element number 1, and the colon minus 1 takes everything up to the last element.
Yeah, exactly. So you're effectively computing the step size. So this would be the dx in the integral. Okay. So this function will compute the integral given the points along the independent variable, so the x, and then also pre-computed points of the function values of the function, which is in this y array. But if we actually need to, on the fly, compute what the values of the function are, we can just extend this integrator a little farther and basically just evaluate it inside. And the one thing that this function buys you is that you can now specify the number of samples you're going to take and the range that you're going to take them over. So this np linspace is a function we touched on briefly yesterday, and it basically creates an evenly spaced, evenly sampled array from value A to value B with n points inside it. So this is basically going to create an evenly spaced grid along your independent variable. And then f is actually a function. So in Python, it's perfectly all right to pass a function to another function as an argument. And in this case, our function could be something as simple as this. Okay, so we can define that and then pass that to the trapzf function. And then the next exercise was just to evaluate both of these. And in the IPython notebook, when you first open it, nothing is evaluated to start off with. So you need to actually evaluate each one of the cells before you get access to the code that's written within it. Yes?
Why didn't you have to import NumPy to do all this?
Could you speak up a bit?
Why didn't you have to import NumPy?
Okay, so because we're using NumPy why didn't I have to?
Yeah.
Exactly. Okay, so that was this command down here, this -- pylab. We'll get into what this does in a little bit, but you can imagine that sort of in your day-to-day workflow, you're going to be importing a lot of the same modules over and over again. So for example, NumPy, and then also your, maybe your plotting function. So basically, pylab is just a short piece of code that loads in commonly used modules for scientific computing. So that's just a shortcut. But you can see that it loaded NumPy as .np, or np, right? So that's how I'm calling the functions in NumPy. np.linspace. Okay, so I'm going to evaluate this cell. So you can see that number went up by 1. Okay, so what this cell did is just compared the result from both of those integration functions. So this one over here and this one over here, just verifying that they got the same result. And there's a one-line definition of the function f of x. Okay, and then what we're going to do is we're going to investigate how the error using the trapezoid rule decreases with respect to the exact value computed using just calculus. And you can, I think it's fairly easy to see that as you decrease the size of the trapezoids, that the error compared to the exact answer will go down. So what we're doing here is we're just instantiating a list with a variety of values for endpoints and just iterating over that. Okay. So what I did was I created an empty list, and for each value in endpoints, what I did was I just added the error, essentially, the value computed using the trapezoid rule minus the exact value, and then just added that. So now I have a list called error, which is the same length as endpoints. And so now I can plot one against the other. Right? So I evaluated that cell. It's a very simple plot. It's basically a plot that has a linear scale in the x-axis and a log scale in the y-axis. And thankfully, all our errors were positive because this doesn't go negative. And that's about it. We put some fancy text up on the title, and that's perfectly okay using Matplotlib's LaTeX environment.
Where did you define exact?
Exact up here is just up here. So that's just, so the integral that we're trying to compute is the following integral, right? So that's just, which is 9. Okay, so we're going to do this again, but we're going to use a little more interesting function. So here it is. And basically what we're going to do is we're going to compute the area under this curve. So we're defining what our limits of integration are using these variables. And basically what we're doing here, you can think of it as something more akin to this. We're just, we're setting two variables at the same line. And that saves a little space, but it's personal preference. And then let me speak a little bit about what we're doing over here. So what we're doing is we're taking all of the values of x and all of the values of y that are between a and b. Okay, so let's say this is so if this is our function, right? We want to just only work with the values that are inside the range that we want to integrate over. Right? And the way that we do that is by using a Boolean mask. So let's break this apart a little bit. Okay, so the notebook's good for a lot of things, but it's not a terminal. So when I want to actually take a look and maybe do function question mark or try to understand what a certain variable is, I like to work in something that looks more like a terminal. And IPython provides that to you. All you have to do is basically just start up this thing called the Qt console.
How did you insert that one above?
I just did, you can go up to insert cell above, and there's also a keyboard shortcut. And all the keyboard shortcuts you can get by doing help keyboard shortcuts. Okay, so let me evaluate this and then go over what all those things mean. So I'll just copy this line over here, because there's a couple things happening on this line at the same time. Okay, all right, so xint is, it's all of the values of the function defined from 1 to 8.5. It's not a very finely sampled grid. We're trying to integrate from 1 to 9. So this is a fairly coarse integration, right? So x greater than or equal to a. So remember, a is just 1. A is the lower limit of integration. So x greater than or equal to a. Basically, for every value in x, it asks, is this value greater than or equal to a? And you can see for the lower values, it's false, and then it becomes true, and it's true for the rest of the array, right? And then likewise, x less than or equal to b is basically saying where the array is less than the upper bound. So then what we want to do is we want to combine these just using Boolean operators. And the way that that I showed you first uses this function, logical and it does exactly what you think it would do, just basically goes element by element and returns true if the first argument and the second argument are true, and false if any of them are false. It's just a normal Boolean and it does that element by element. So now we have another Boolean array. Just to mention, this isn't the only way of performing that operation. You can also do something that's a little more compact. And that gives the same value, right? Okay, so now that we have this Boolean array, and I'll just give it a new name. So b, oh crap, I overloaded b. All right. Okay, so here's my Boolean array. Then what I can do is basically just use that to return a subset of another array. So I've got x, right? So this basically returns all of the values of x where the Boolean, where BL is true. Okay, so that's basically just taking a subset of x, right? Let's page up till we get to the original line. All right, so this was the original line. And then the last thing that's going on this line is that we're slicing it, okay? And are people clear what this : 30 means? What is that doing?
Chunks of 30.
Yeah. So this : 30 is basically starting at the 0th element and then skipping by 30s, all right? So we have a length 200 array, but we're only returning every 30th element. So our array is very coarsely sampled. So xint, if we look at the size of that and look at the size of x, we're going from 200 down to 6. All right, let's look back at the notebook. Okay, and basically we're just plotting, making a plot of the function and showing the our integration. And finally, the last thing is basically to say, like, it was fairly easy to to write our own integrator using the trapezoid rule. But in sort of general, in your general coding life, you don't want to do that. You just want to use something that's been written already, because there are much more sophisticated and numerically accurate ways and numerically fast ways to compute the area under a curve. And one of these, they're contained in this scipy.integrate module. So if we take a look at that, scipy.integrate, remember that if you're curious about what a module does, you can just query up the doc string. All right, and this gives you sort of a high-level list of the integration tools that it gives you. And without going into detail, these are a lot more sophisticated and will give you a much more accurate result than the trapezoid rule. So here is the integrate the integral computing using this quad routine. You can see that it's very close to the exact value. This is the error on that, and then using the trapezoid rule with 6 points gives you something that looks like it has about 10% fractional error. So the quad routine actually works faster than your own trapezoid routine. All right, so let's move over to the homework solutions. Okay, so the first thing that we want to do is load up the data that's in this CSV file. And there's a convenient function called CSV to rec that will basically read in a CSV file and put it into a record array. And I'll sort of go into briefly what each of those functions are and what a record array is. So if I fire up the Qt console again, and then take a look at CSV to rec, just query it, you get a nice little description of what it does. But if you look in sort of one of the first lines, you can see where that module came from. And this module came from the matplotlib package and then the mlab submodule. And this is one of these things that was imported when we did --pylab. So what --pylab effectively did was said from matplotlib dot mlab import star, right? And it loaded all of the functions in the matplotlib.mlab submodule into the namespace. Now, okay, so that's what CSV to rec does. Now let's talk about what a record array is. So if I just hit enter in my Qt in my notebook, I get sort of a view of what this data is. So you see that there's dates in here, there's integers, and then at the end, there's a sort of description of what each one of those data elements are. So you've probably worked with data like this before, but just to make sure that you understand what it is this data one-dimensional or two-dimensional? What's the dimensionality of this data set?
One-dimensional.
Okay, one. Anybody want to disagree? Okay, so I heard one and two-dimensional, and the correct answer is it's one dimensional. But the reason why it's easy to make that mistake is that you're accustomed to seeing this data, in a table, like an Excel table. So basically, there's rows of data, so like row 1, row 2, and then you have your columns or your keys. So this would be your different values, and then each one of these has some sort of value in here, right? This could be like a name and a time, right? But the data structure itself is in fact one-dimensional, and each one of these different columns are just related one-dimensional quantities. So if we ask this record array, if we run the ndim function, which just returns the dimensionality, you get 1. Okay, so we have all this data in a nice record array. Now we want to plot it. So like I said before, the matplotlib, the --pylab option, when we fired up the IPython notebook, loaded a bunch of things into the top-level namespace. One of these functions is called plot. Just to give you a simple example of what plot does. As always, you can, do the question mark and give yourself, a high-level introduction to what the function does. But we can just give it a simple example. And there's x squared. Okay. Okay. So we want to plot this this data up, and basically to do that, I just called the plot command several times. Matplotlib knows how to interpret the date-time type, and then here are all the different time series colored in different colors. And essentially, what this does, when you call plot several times, it assumes that you don't actually want a new window unless you specify it. It just assumes that you want to plot over what you've already plotted. So, if you're used to using IDL, this would be like oplot. And then the nice thing about this plot function is that there's a keyword argument called label, and you just pass it a string. And it's basically, you can label any so-called artist in matplotlib. So I've just given these, all of these a label, and then at the end, I just ran this legend command with no arguments, and it gave me sort of a fairly ordinary looking legend. And if I wanted to make this thing look nicer, you can imagine that there are tons of options that you could do to make it look as pretty as you want. And one of the nice things about record arrays is you can iterate over the values. So in many ways, they're like a dictionary. They have a key, which is the column name, K1, K2, and they have a value, which is all the values in the row. So one way to make this plot a little more economically in terms of lines of code is to just iterate over the values. So that's what I did over here. I just defined all the names that I wanted to plot as a list, and then I iterated over them for name in names, and then basically plotted week start against all the different values, set the label, and ran the legend command.
If you don't want to overplot, how do you do it?
So if you want to create a new plot, so since I'm not working interactively, this isn't going to be particularly obvious, but I can just start a new version. Okay, so this is what you get when you just type this into your IPython shell, or your IPython interpreter. If I want to clear this plot, I just run this command, and that clears it. And now I'm ready to plot again. And you can see that every time I plot a new function, it's just changing the color. So it's overplotting. But if you want, if you want two windows, then you have to open up a new figure like that. And then you actually need to refer to these figures sort of individually. So there's a concept in matplotlib called the current figure, and the current figure is basically the last one you used. And for most of your work, you basically want to be referring to the current figure.
How'd you refer to it?
There's a command called get current figure, and that's the object. Matplotlib is very rich, very complex. This is only a quick introduction. If you'd like to know more, you can talk to one of the counselors. We might be getting into more of that later anyway. Okay, so then the next problem asked to return the minimum and the maximum value for one of the columns. I think it was spring. Oh, it was all of the columns. So we want to figure out at what week did the peak interest in this topic happen, and at what week did hardly anybody care about it at all. So the function that we use to figure out this is called argmax, right? But if you didn't know it, let me sort of walk you through how you might find it. Okay. So again, I'm going to go to the Qt console, right? And what I'm interested in is the maximum value. So, since I'm working with an array, I might, put in a numpy and then max and then question mark, all right? And basically, okay, so I can read this. It says return the maximum of an array. Okay, so that's close to what I want, right? I want the week at which the value was the maximum, but I don't want the maximum value itself, right? Or I want both quantities. So I can read this doc string a little more, and what it has is this sort of see also, these functions that are sort of related. And so I can read that and I go, oh, argmax, that's the indices of the maximum values. Okay, so that's actually what I want. Okay, so if I run this, I'm basically finding the maximum value, and then this is the index of the array where the maximum value, maximum interest in spring break occurred, and this is just a string telling you that. So again, I can loop over the keys in an array just by referring to them by their string name, and I've done that here. So I'm basically getting the maximum value using this argmax function, minimum value using the argmin function, and then just printing them out like this. And this just means tack on white spaces to the right side of a word up to a certain length, and that just makes the table a little prettier. Oh, sorry. Well, I'm attaching the characters to the right side of the word. So yeah, left justification. Okay, so now we're going to do some basic statistics. Basically, the problem was to answer what term has the largest scatter about the median value. So scatter about the median value could mean a few different things. It could be standard deviation. It could be median absolute deviation, and I did the latter. And so again, I'm just iterating over names. All right, I'm pulling out the specific column with that name. I'm computing the median. Then I'm subtracting the median off of that value, off of that array, computing the absolute value, and then computing the median value of all of that. Right? And then for each one of them, I just print it out, and you can see that textbooks had the minimum scatter, and Kayak had the most scatter.
Sorry.
Sure.
For the previous problem, I thought that the homework said to find the maximum for every year.
Okay.
The way I was done with the
Yeah, you're right. Okay, so I misread that. So in order to do max and min for a given year, you need to select sub-regions of that particular array. So you could say, you could basically do what we were doing before in the integrate example, and basically query all of the indices for a particular year, and then basically do that again. So I actually just misread the problem.
Other question?
So I'm running a little short on time. I want to stay on time, so let's hold those until the end. And then the last problem was basically to evaluate what the correlation was between these two trends. And if you're not familiar with what a correlation is, essentially you've got a function that's peaked, and you want to correlate that with another function. Basically, what a correlation is it it slides one of these arrays past the other, and then computes the product element-wise, and then sums that. All right, so it's a measure of basically gives you a degree of how well each one of the arrays line up. It's peaked sort of in the middle because since this function is everywhere positive, you're going to get the maximum sum when they're sort of right on top of each other. But you see all of these sub-peaks, and that happens because one of the functions, because the functions have a very similar peak structure. There's one peak per year, and when you slide them past each other, when you slide by the correct delay, you get a maximum. And so basically, I did the same argmax function on the result of the correlation for just 1 year, located that peak, and basically determined that the peak occurs when you've displaced the two arrays by 33 elements, or 33 weeks. Okay, all right, so now we'll take a few questions. All right, well.
So about argmax.
Yeah.
So the way that you called it, you were basically saying np.argmax for whatever, trans name, whatever. And can you also use argmax as like a property of trans? Is that the same?
Yeah, it's exactly the same. So yeah, there's sort of a couple ways to call a few functions in using ND arrays. So we can take a look at this in the Qt console. Let's just look at the result array. That was the last array that we worked with. So argmax works in this way, which is how I was doing it. All right, but if you type the array in IPython and then you hit tab, what it gives you is a list of all of the methods and attributes that are attached to an ND array, right? So attributes, basically, we'll get into this later today, tell you something about the object, okay? So I think there's an attribute called ndim, right? So that gives you the dimensionality. But there are other things like attributes called methods, which are basically things that object can do. And one of the things that this object can do is tell you the index of the maximum value, okay? So that basically calls the same code, but one of them is more object-oriented and one is sort of more procedural-oriented. Who's giving the next talk? How are we doing on time? Okay. All right, up there.
So when you do correlation, it seems a bit strange to me. So it looks like you correlate spring break and spring break. And it's strange that the correlation is not maximum at 0. Because if you correlate two things and you don't have displacement, the correlation should be maximum.
Oh, whoops. I did correlate spring break and spring break.
Exactly, that's the thing. Then the maximum should be at 0.
So the maximum is at 0 displacement, but the way that, So the way that the result works, and this is sort of just a convention, is let's see. So let me space this out a little better. All right. So the result. So this first correlation result, the first correlation you can do is when there's just one overlap. Okay. There's one overlapping element. So it's displaced by the length of the array minus 1, right? And this value goes into result 0, all right? Then this one gets shifted over by one element. You compute the correlation again, and that one goes into result 1, okay? So the maximum should occur when it's shifted by, the length, right? So this is just a convention with how this particular implementation of the correlation is defined.
Right, so that's what I mean. So the maximum on your graph is where they both are exactly the same, right? So that means that the maximum correlation, so the lag you need to plot is not where you plot it, but it's somewhere near the middle, the next peak of the middle.
Yeah, so if you were interested in plotting something like a lag, let's see. So let's take a look at. All right, so we can take a look at the length of result, right? So result.size, so that's another attribute of an array. And then we can do, if you're interested in doing like a lag, we can do result size. Let's see. Okay, so now it's going from a negative value to a positive value. So we've just shifted it. It's just in our definition of what our independent variable is. Okay, and don't pay attention to the vertical line anymore. But I've just shifted everything on the plot so that the peak is at 0.
Yeah, now it's more meaningful.
Yeah.
just listen.
So, all right, so I think I see why this was confusing. First, so what I did was I just plotted result. And when you plot something with only one iterable, right, or only one array, it assumes that the array that you want to plot is the independent variable, the y variable. And as an x variable, it just basically goes from 0 up to the length. So it basically it plots the same thing as a range result dot size, right? So that's just what plot is assuming you meant. So it's basically plotting value versus index, okay? But I agree that plotting against something like a lag makes more sense.
Some of this, as well as some stuff you were doing yesterday, you end up with these long function names of like whatever dot, whatever dot. And if you're doing a lot of analysis all using some of the packages, what's a typical way of shortening down those?
So the question was, so we're, with Python is very modular, and if you have a complex module, you might have submodules of submodules of modules, right? So the question was, how can we shorten the name or make it easier, to use? And we've actually already been doing some of those tricks, but they might have been sort of behind the scenes. So one of the functions that we used today was called CSV to rec, right? And basically, the way to get at this function, if you were to just sort of doing it, using the sort of standard way, would be you would import matplotlib.mlab. Okay, so that I've imported that, and then now to call this function, I would do this. Okay, so that's pretty long, and you know, you don't want to be typing like, you know, those 20 characters all the time. So it's perfectly all right to do from matplotlib import csv to rec. Okay, so that's imported this function, and now to call it, you can only you know, type csv to rec. Or if you want to be even more slick, you can basically on the fly rename what this function is. All right, so csv to rec is f. All right, so now that entire line is collapsed to one character, and then I can basically do the same thing with just that function. All right, great. And then the next exercise was just to evaluate both of these. And in the IPython notebook, when you first open it, nothing is evaluated to start off with. So you need to actually evaluate each one of the cells before you get access to the code that's written within it. Yes?
Why didn't you have to import numpy to do all this?
Could you speak up a bit?
Why didn't you have to import numpy?
Okay, so because we're using numpy why didn't I have to? Exactly. Okay, so that was this command down here, this --pylab. We'll get into what this does in a little bit, but you can imagine that sort of in your day-to-day workflow, you're going to be importing a lot of the same modules over and over again. So for example, numpy, and then also your, you know, maybe your plotting function. So basically, pylab is just you know, a short piece of code that loads in commonly used modules for scientific computing. So that's just a shortcut. But you can see that it loaded numpy as .np, or np, right? So that's how I'm calling the functions in numpy. np.linspace. The points along the independent variable, so the x, and then also pre-computed points of the function, values of the function, which is in this y array. But if we actually need to, on the fly, compute what the values of the function are, we can just extend this integrator a little farther and basically just evaluate it inside. And the one thing that this function buys you is that you can now specify the number of samples you're going to take and the range that you're going to take them over. So this np linspace is a function we touched on briefly yesterday, and it basically creates an evenly spaced, evenly sampled array from value A to value B with endpoints inside it. So this is basically going to create an evenly spaced grid along your independent variable. And then f is actually a function. So in Python, it's perfectly all right to pass a function to another function as an argument. And in this case, you know, our function could be something as simple as this. Okay, so we can define that and then pass that to the trapzf function. Okay, so I'm going to evaluate this cell. So you can see that number went up by 1. Okay, so what this cell did is just compared the result from both of those integration functions. So this one over here and this one over here, just verifying that they got the same result. And there's a one-line definition of the function f of x. Okay, and then what we're going to do is we're going to investigate how the error using the trapezoid rule decreases with respect to the exact value computed using just calculus. And you can, I think it's fairly easy to see that as you decrease the size of the of the trapezoids, that the error compared to the exact answer will go down. So what we're doing here is we're just instantiating a list with a variety of values for endpoints and just iterating over that. Okay? So what I did was I created an empty list, and for each value in endpoints, what I did was I just added the error, essentially, the value. So the trapezoid rule is sort of the next level of sophistication to computing the area under a curve beyond just the strict Riemann sum. So you're basically, with the trapezoid rule, you're just computing the average value at a bunch of different step sizes and then summing those up times the width of the step. So coding this up is fairly simple. It's a one-line, it's essentially a one-line call. And the only thing that you need to be sure that you understand about this piece of code over here is the way that the slicing syntax works. So is everyone clear on what this 1 colon and colon minus 1 do? All right. Would somebody care to explain what that does? Sure.
So the 1 colon takes everything starting with element number 1, and the colon minus 1 takes everything up to the last element.
Yeah, exactly. So you're effectively computing the step size. So this would be the dx in the integral. Okay. So this function will compute the integral given. All right, let's get started. So I'm going to briefly go over solutions to the breakout section that we started on yesterday afternoon. And in case you don't know, I'm Eric Pettigura. I'm one of the counselors here. All right, so we're going to be working in IPython. So from my terminal, this is the directory where my notebooks are stored. You see them here, trapezoid rule and homework 1 solutions. We'll be going over that later. So I'm going to fire up the IPython notebook with this incantation here. And then notice this -- pylab inline. And inline basically lets you display plots right in the notebook.
Eric, can you get some of the lights?
Sure.
In the middle of the chalkboard. Below the middle of the chalkboard. Just to your right.
Oh, okay. Here.
Yeah.
That good? All right, so we're going to fire up the IPython notebook. It's going to open up a web browser, and let's take a look at the solutions.